you've already met Susan Houghton. She is going to be helping us moderate the session today and make sure we're monitoring the chats and getting folks situated. So thank you, Susan. She's going to help manage questions too. I want to introduce Kevin Greer from the school district. He's Director of Curriculum and Instruction. He's been instrumental in putting this together. And Nadine Horner from the lab is part of the community relations team. There's Nadine. And of course, our featured speaker, Dr. Megan Bruck Syal. So Megan, thank you so much for being here. We're really excited. This is our first one, so bear with us, but thank you for taking the time out of everybody's very busy schedules to learn a little bit about planetary defense today. So I think, am I looking, Susan, do we have, if we could share the next slide, that would be great. As I mentioned, this is the first of 4 Ask a Scientist events that we're hosting. So just wanted to make sure everybody was aware that there were 3 more coming. It's over the next 2 weeks, always at 1 o'clock on a Tuesday or a Thursday. So there is information on the Foundation's website if you're interested in signing up for more of them. So next slide, just some quick housekeeping rules. I think by this point in our shelter in place across the country, people are familiar with Zoom, but if not, just everybody again will be muted during the presentation except for the speakers. If you have a question or a comment, please go ahead and use the chat feature, which should be along the bottom of your screen. And Susan will be reviewing those throughout the hour so that we make sure we can try to address everybody's questions. If we get an opportunity to, and somebody really wants to say something, and we have an ability to unmute you and be a little more interactive, but we'll have to just see how that goes today. We are also recording today's event, so we'll be sending out the link to the recording afterwards. So next slide. Again, today's discussion is all about planetary defense. I'll admit it's a topic I did not know much about myself when this got underway, but it's something that's actually really timely and relevant to everybody, and it's something that we should all learn more about. This is a slide that just shows, there was a recent article in National Geographic talking about this very thing, and Megan is in fact quoted in it, the idea that there is a large asteroid that's coming within a certain radius of Earth that scientists are aware of and trying to use as an opportunity to test our defensive systems against a potential impact situation. And Megan can talk more about that as we get into it. A little bit about Megan. She lives right here in Livermore with her husband and 2 young boys and their dog Ginny, who we're hoping might make an appearance at some point in the presentation. She's been at Lawrence Livermore National Lab for 5.5 years, and she's a true expert in this field, and we're really lucky to have her with us today. And on top of all of that, she's also an accomplished runner. She's completed the Boston Marathon twice, which blew us both away, all of us away. So without further ado, I'd like to hand things over to Megan. And Megan, maybe we can just get started with, you could share a little bit about the process of making the video that everybody has seen. It was really cool how you conducted those experiments right in your backyard, and maybe you can talk a little bit about what went into that. Thank you.
Sure. Yeah, great, thanks a lot. Yeah, my dog Jenny is here, so she's just being silly, but if you haven't had a chance to look at the video yet, I introduced the idea of asteroids that might impact the Earth and how those of us that work in planetary defense try to prevent that from happening. And a lot of our work is done on supercomputers at Lawrence Livermore, but we also use impact experiments to learn more about real-world response, and we need to be able to compare our supercomputer simulations to real experiments to make sure we're getting the right kinds of answers. So the backyard experiment, we looked at 2 different types of target materials that you could buy just from a garden shop, sand and perlite. And the difference, one of the big differences between those materials is their porosity. So perlite is really fluffy. It's like those Dippin' Dots ice cream that you might buy. There's a lot of void space inside of it, which means that when a spacecraft impacts it, that a lot of energy is lost to crushing of material. Another way to think about porosity is when you wear a bike helmet, there's styrofoam in that that's porous, and that absorbs a shock wave that you would get if you fell off your bike at high speed and need to protect your brain. And that shock wave attenuation, a lot of it's happening through the crushing up of pore space. And the same thing happens if a spacecraft is going to impact a porous asteroid, and the shock wave is attenuated by the porous rocks on the asteroid. And we know that a lot of asteroids are very porous. They're very collisionally processed. We describe them often as having rubble pile type structures. So like a mixed bag of rocks of different sizes and a lot of void space in between, which is really interesting. And a lot of spacecraft have visited asteroids to learn more. And right now we have one in orbit around asteroid Bennu called OSIRIS-REx that's studying lots of details about that asteroid. And another mission called Hayabusa 2, led by the Japanese, is returning samples from asteroid Ryugu. OSIRIS-REx plans to bring samples back from Bennu as well. And so we're always studying more about the real properties of asteroids. But the experiment in the backyard, I hope, was illustrative to see how different asteroid materials would respond differently. And on Earth, we know those aren't exactly what the conditions would look like at an asteroid. So we use simplified terrestrial materials we find here on Earth to represent some of the differences. And with that, I guess I could go into some of the questions we received from students. Or
Sure. Yeah, no, thank you to everyone who submitted questions in advance. Maybe we can start with the one from Shane that we received. He asked, how have planetary defense systems evolved over the years with new types of technology and information?
Yeah, that's a really great question. Planetary defense as a field of study didn't really start to develop until the early 1990s, when more and more near-Earth objects, or NEOs, asteroids and comets that come in close distance to the Earth, started to be discovered by telescopes. So as telescopic capabilities became greater, we got to discover more and more asteroids. And in the early 90s, the threat began to be more apparent. And also another event that was really interesting at the time was the impact of Comet Shoemaker-Levy 9, which impacted Jupiter in 1992. It was imaged by the Hubble Space Telescope and also the Galileo spacecraft that was en route to Jupiter at that time. That was the first time we had imaged in real time an asteroid or comet impact, in this instance a comet. So comets are icier versions of asteroids. Impacting a real planet in real time, which was really cool to see it break up as it entered Jupiter's atmosphere. And that really called attention to, well, it can hit the other planets, it can hit Earth too, and what is our plan for that? What do we have to do to be prepared? And it was recognized from the very beginning that the fast push methods like kinetic impact or nuclear explosion are the only ones that will work for some of the bigger, more dangerous asteroids. And for a lot of the bigger dangerous asteroids, particularly ones with short warning times, the only method that will work, and this is because you can only transport so much mass to an asteroid with a given rocket. So our rocket capabilities are always advancing on Earth. The US has spent a lot of money in developing next generation technology, but you can still only get so much mass. It's very expensive to put mass at an asteroid. And so you need a very concentrated form of energy. And one of the most concentrated forms or the most concentrated form of energy that we have is nuclear energy. And so the nuclear energy in the form of a nuclear explosion is the most mass efficient way to deliver a momentum delivery, deliver a momentum impulse to an asteroid when needed. So there are some asteroids that are so big, or the warning times are so short, that is the only method that will work. And that was recognized from the beginning. But what's happened, and this is what your question's really getting to, so it's a roundabout answer, but in the last 30 years, our understanding of asteroid properties has really evolved with all these different missions to asteroids. We have a better feel for how to model them correctly. And also our abilities to simulate using supercomputers have evolved quite a bit. And that's due partly to Moore's Law. If you've heard of Moore's Law, it comes from Gordon Moore, one of the founders of Intel. It means the number of transistors on an integrated circuit doubles every 2 years. And so the computing power in our phones today, an iPhone, far exceeds what could fill a whole, what used to fill a whole room of computers in the past. And that's because, and with that increasing capability, we're able to do simulations at higher resolution, and higher dimensions, particularly 3D simulations. And so now we have a much better way of modeling asteroid response to any of these deflection techniques.
That's really very, very cool. Thanks, Shane, for your question. We learned a lot from that. Another question we had sort of related to that was, twofold really. What is the probability of a significant impact event on Earth, and what does that look like, and how far in advance might you have to plan for these things?
Yeah, thinking about the probability of an asteroid impact at Earth is challenging. It's a little bit how we would approach thinking about the probability of a big earthquake. So that the probability, we can say on average, an earthquake of a certain size or an asteroid of a certain size will occur every so many years. But that doesn't necessarily mean just because one happened 10 years ago that we know exactly when the next one will happen. And that's because each event is independent from each other. And scientists when they're trying to describe phenomena like this, discrete events that are independent from each other, they use something called a Poisson distribution, Poisson. And if you end up taking some probability or statistics in college, you'll probably be introduced to some of the equations that govern a Poisson distribution. But what it basically means is that we can say something, for an example, the Tunguska impact occurred in 1908 in Siberia, in a very remote part of Russia. It devastated 2,000 square kilometers of forest. So if it happened over an urban area, it would have killed a lot of people and destroyed a lot of infrastructure, been really terrible. Luckily it didn't. But just because that happened, now that was about 70 meters or so, and on average, we think those kinds of events happen every few hundred years. But just because it happened in 1908 doesn't mean we have to wait a few hundred years for the next one to occur. They're all independent. It's just on average, we can say they do have an average time interval. And so thinking about those time intervals is a little bit challenging. But something very, very big, like the impact that took out the dinosaurs, 65 million years ago, the Chicxulub impact, which occurred in the Gulf of Mexico. That was really big. That was like 10 kilometers in diameter, and those only happen on average every 100 million years or so. And the other constraint that we have is the big asteroids are easier to observe with telescopes, and most of them are well characterized that are above a certain size, and we know they're not going to be a threat to the Earth anytime soon. So we worry more about the ones that are in the tens to hundreds of meter size, which could still be very damaging, but they wouldn't be like a extinction level event probably.
Mm-hmm. Great. Thanks so much. I'll turn to another question from Rosendo that was submitted. Thank you. Have humans actually been able to stop an asteroid from hurtling to Earth?
That's a great question. Luckily, we haven't had a reason to try to stop one yet. So the most recent big one that occurred, I just mentioned, Tunguska in 1908. That's big enough that if today something were coming, now that we have spacefaring nations, we might try to do something about it. Of course, in 1908, there were no space programs. Space flight only began in the late 1950s. And so, today we're hoping to be prepared for the next Tunguska or the next thing that's even bigger than that potentially. And one thing that we can do today, and we've done, observers have done successfully, is predict small asteroids that are going to impact the Earth and track them. Below a certain size, you wouldn't try to stage a deflection. You would just want to know where it's impacting to evacuate the area or warn people not to go near windows, for example. Like the Chelyabinsk impact in 2013 in Russia, that was not super big. It was 17 meters across. It blew out a lot of windows. and a lot of people were injured. And if they had known even a little bit ahead of time, they could have told people, don't stand by your windows, because people see a bright flash in the sky, and the first response is they want to go to the window to see what it is, but then a blast wave comes and they're injured. So we're hoping to be better prepared for events like that. But for this even smaller things, they've been able to have some examples. One example was, I think, 2014, Asteroid 2014 AA in a few years ago. They were able to track that one before, a few days before it impacted, and predict that it was going to impact the Atlantic Ocean. So they're able to track it, and then infrasound is able to also determine it did impact the ocean. So they're getting really good at tracking those asteroids at late times now.
How that prompts me to think about how you communicate with sort of the global community of planetary defense scientists that are out there. I know a lot is happening at Lawrence Livermore Lab, but how many of you scientists like you are out there, and how do you guys communicate about these events?
Yeah, this week, actually, you'd mentioned the DART mission that they had done a National Geographic article on recently. We're having a meeting, a Zoom meeting, actually, all this week just on the DART mission. And so I'm part of the investigation team. Several of us at Livermore are contributing simulations to that mission. And so that's people all over the world. There's people in Japan, people all over Europe, people all over the United States and Canada contributing, and a lot of other countries, probably some in South America too. Planetary defense, as you might imagine, is a very international effort, because any country could be affected by it. And so there's a lot of collaboration on space missions like this, and for the very important work of tracking asteroid orbits and making sure there's a global database that's keeping all that information together. NASA's Jet Propulsion Laboratory does a lot of that work. Their Center for Near Earth Object Studies, that's a really good website. I recommend you visit if you're interested in learning more. They have a lot of really cool tools to look at visualizing the near Earth asteroid population, and how our understanding of it has grown over the last few decades. So yeah, there's a lot of people that work to pull in all the observations from various telescopes to make sure everyone has access to the data that needs it.
Very cool. Susan, have we gotten any new questions that have come in? I want to make sure.
We absolutely do. So Megan, here's a question that came in. How did you guide your high school and college studies to prepare for this field? And what was there a moment in your high school or junior high or college career that you had that epiphany and said, aha, this is what I'm going to be doing?
Yeah, that's a great question. I think going back to elementary school, I was always really interested in actually all of my classes. I didn't favor one over another. I loved writing and I loved science and math. But I really loved focusing on research, and even some of the early research projects I did when I was 9 or 10 years old. I liked digging deep in one area. And then as I got into high school, when I took calculus and physics, I felt just this really just overwhelming sense of, wow, this is so elegant and so descriptive of so many things in our world, that how can you not want to learn all that you can? And that made me feel like I really wanted to study a lot more physics and a lot more math. And then in college, I majored in astrophysics and mathematics, because I had always liked space science, so I took a lot of astronomy and astrophysics classes. Most astronomy classes, to get to a certain level of understanding, you have to have a physics background. So there's a lot of physics in most areas of astronomy. A big epiphany for me came in college when my future PhD advisor visited. This was in 2005 or 2006. It was right after the Deep Impact mission happened. That was the first time they had done an impact experiment at a small body. This was at the Temple 1 comet in 2005. They launched a copper projectile at this comet, and were able to observe this giant impact ejecta curtain that came out, and it was just so incredibly beautiful. And they learned so much by excavating material from this exotic world, this comet that no one had ever visited before until the spacecraft got up real close to it. And that combined with learning more about how we use impact craters to study the histories of planetary bodies all over our solar system really drew me into impact physics and wanting to study with my PhD advisor at Brown University. And I think that's a really good lesson in when you're looking for schools, either undergrad or grad schools. If it's hard to pick based on the people that you're planning to work with, not necessarily the name of the college. That can be important and open doors, but the people that you work with closely will really define your experience. And so making sure you have a good fit with your advisors is really key.
We have another one from Akshay, who has sent us an email, and she or he want to know basically about asteroids. And let's go up to their question right here. And how do you track an asteroid, Megan? Is it complicated?
Yeah, that's actually not something that I have done myself. I work with a lot of people, collaborators at other institutions that do that. And it is complicated. The big contributors to discovering new asteroids are Catalina Sky Survey at University of Arizona and Pan-STARRS in Hawaii. And what's complicated about observing them is that you can't just observe them once. You need to observe them multiple times, do follow-up observations to really constrain the orbit very carefully to know exactly what its position and what its velocity is, so we can predict where it's going to be in the future. And asteroids are also subject to other external forces, like the sun. The sun shines down on the asteroid, and some sunlight is re-radiated away, and that provides a little push. And all asteroids rotate also. They're not spherical. They have funny shapes. Some are bilobate, so they have two lobes, like a bowling pin, or any number of funny shapes. And so the way that their spin rates and their trajectories evolve can be complicated. So observing it at one point in time isn't enough. You need to do follow-up observations, and then many years later to confirm that it's still going to be on the trajectory you think it's going to be on, do more. And also asteroids occasionally impact each other and create new debris fields. Sometimes they're active. There's water ices inside of them that vaporize when they come close to the sun. The difference between comets and asteroids is not as clear as we once thought that it was. So there's kind of a spectrum of bodies that have ice and rock or some combination of them between comets and asteroids, and they can evolve in really surprising ways. So yeah, I would say overall it is pretty complicated to track asteroids, but there's a lot of specialized software that is written to help astronomers track them consistently and be able to share their data with the whole community today.
So Sally and Megan, we have another question following up on that supercomputing reference. And this is from a student who wants to know, is there a planetary defense problem that might be too big or too complex to simulate on today's supercomputers?
Great question.
Yeah, that's a really good question. There are some that really push our limits. I would say modeling the DART spacecraft impacting asteroid Didymos is really interesting. I'll provide a little more background on DART because I didn't discuss it in the video earlier. This is just the coolest thing ever. It is a double asteroid. So there's one bigger asteroid, it's 800 meters across, and there's a smaller asteroid 150 meters across orbiting it. So it's a binary. And a lot of asteroid systems are actually in binaries, or even triple asteroids sometimes. But what we're going to do with the DART spacecraft is going to impact the smaller one, and it's going to nudge it a little bit, not that much, something on the order of 1 millimeter per second change in velocity, so that its orbital period, the time it takes to go around the bigger asteroid will change. And we'll be able to measure that from Earth-based telescopes. And because it's a double asteroid, we get that really precise measurement of the deflection efficiency, whether it's a millimeter per second or slightly bigger or larger than that. But that's 150 meters asteroid, and the DART spacecraft is kind of like an aluminum, mostly aluminum box with two big solar panels. It uses solar electronic propulsion, so it's got these giant solar panels, and it's got a kind of complex shape, and we want to model all of that correctly using the right materials. And so a lot of work has gone into making sure we can resolve all the parts of the spacecraft very finely, which requires on the order of centimeter resolution, few centimeter resolution, going into an asteroid where we want to model in high resolution the impact site, but we also want to model the rest of the asteroid because it's small enough that stress waves will propagate through to the back of the asteroid and interact in complex ways. So we don't want to just model right where it is. We want to model the entire asteroid if possible. And that requires getting that fine resolution right by the spacecraft, but also to include all of the asteroid is really challenging. So that's pushing our computer capabilities to their limits. Some of the other models that really push us to our limits are including realistic structures in the asteroid. So a rubble pile structure, one way of including that was developed by Mike Owen, who's one of my colleagues at the lab. He actually used some video game visualization software to find a way of stuffing boulders of different sizes into an arbitrary shape. And so you can use an ellipsoid, like an elongated sphere, stuffed with boulders of various sizes. They follow a kind of power law size distribution. So there's lots of little boulders and fewer big boulders. You can put them in randomly and then fill the space in between. Or you could use a very complicated shape, like a real asteroid's shape, like asteroid Itokawa that was visited by Hayabusa 1 by the Japanese, or we use a lot of radar-derived shape models. Glovka is another weird shape we use to look at shape effects sometimes. So including all that detailed structure at high resolution is also really challenging. So we're always trying to push the limits of what we can do given current computer capabilities.
We have another one, Sally and Megan, from a student who wants to understand the size versus impact potential on the Earth's surface of a possible asteroid. I mean, what are we talking about size-wise and impact-wise? What would that happen, assuming that the material makeup were fine?
So can you just read it one more time just to make sure I answered?
Okay, but what is the size we're talking about? If there was a potential for an event to occur on the Earth's surface, what could it possibly be? As big as the United States? What would it be? What size would it be? And
okay.
What is the impact potential of how far down it might create in terms of a crater?
Okay, yeah, that's a really good question. So on the range of sizes, the really big ones, like the one that took out the dinosaurs, that's 10 kilometers across, like the size of a city like San Francisco. Those are not a threat. We can observe all of the asteroids that size, and they're not going to impact us anytime soon. But as you go smaller in size, there begins to be many that have not been observed by telescopes yet. And we know that we're missing them because we have pretty good models about what should be out there based on repeat observations or repeated observations of the sky, and what we have an idea of what we're missing. So if you get to a kilometer in size, 95% of those are well constrained. So there's very few that are missing that could be a threat. As you get down to the hundreds of meters size to something that's the target for the DART mission, Didymos B, the smaller asteroid in that system, it's 150 meters across. There's about 25,000 of those out there. We have about 30% of them observed. So they're missing most of them that are that size, and something that size could devastate a whole region. It could do really a lot of damage. And so you're not quite looking at the gigatons of energy delivered, but I think that's in the maybe tens to hundreds of megatons of energy. So lots and lots of energy, could be very devastating. So the range is not to the range is really anything from Chelyabinsk in 2013 that blew out all those windows. That wouldn't be something we try to deflect. We try to warn people. That's about 17 meters across, all the way up to a kilometer at the most is kind of what we're concerned about. But most of the ones are in the tens to hundreds of meters size that are really concerning right now.
We have another question from Alana, who wants to know, are you ever worried about space debris, or is it just asteroids?
Yeah, space debris is a really big problem for a lot of satellites and other spacecraft that are in low Earth orbit. It's something that's well studied by folks at the lab and elsewhere. I believe there's people at the lab working on that. But it's not a major issue for planetary defense because the size of most space debris is relatively small, so that it would burn up in the atmosphere before it impacted Earth. Space debris is more of a threat because most of it's moving at very high speeds while it's orbiting the Earth. Even small things that are millimeters in size, if they impact a spacecraft, they can do damage to it. So a lot of satellites and spacecraft have a lot of shielding for that reason, so that small particles that impact them, they won't damage them severely. But yeah, that is a really interesting problem that a lot of people are working on.
Sally and Megan, another question has come in that since you referenced the ice that are on asteroids, is there evidence of any previous organic matter or life that you've seen on asteroids?
That's a really interesting question. And there's been missions to visit asteroids that were believed to be enriched in organics or water. Those two asteroids that I mentioned earlier, asteroid Bennu and asteroid Ryugu, are both C-type asteroids, which stands for carbonaceous asteroids. That doesn't necessarily mean they have a lot of carbon, but it means that they're some of the most primitive asteroids in the solar system. And so they haven't been very processed by heating. And the hope is that they preserve a lot of the early conditions of our solar system. And so for folks looking to learn more about what were some of those precursor molecules, before life existed on Earth, for example, they're really interested in looking at C-type asteroids. There's another mission called Dawn that went to visited asteroids Vesta and Ceres, which are really big asteroids in the asteroid belt. And I should mention that the near-Earth asteroids that we worry about impacting the Earth don't reside in the asteroid belt. They've been perturbed by Jupiter or something else to come close to the Earth and be possibly a threat. But most of the asteroids, a far majority of them, live out in the asteroid belt, which is in between Mars and Jupiter. They're safely far away. And some of the biggest asteroids are Ceres and Vesta. Those are some of the first asteroids ever observed. And Ceres in particular has a good amount of ice there. And there's no evidence of life or previous life, but these bodies are of interest for whether they could deliver life relevant materials to different planets. So that's something I've looked at in the past, is delivery of organics or water to different planets from asteroids or comets is a big question. Where it came from, how that happened early on in the solar system's history.
We have two more questions for you, Megan. One is a follow-up question to your reference on the nuclear explosions causing the greatest impact on asteroids. And this person wants to understand if there would be any issues with nuclear detonation in space and how widespread radiation might be, or would it disperse immediately? What are the cause and effect of that?
Yeah, when this would be deployed, it would be very far away from Earth, and astronomical scales are really hard for us humans to kind of internalize and think about because they're so big compared to anything we see here on planet Earth. But the scales are so large that the radiation you get from eating a banana, because there's a little bit of radioactive material in a banana, would be greater than any radiation you'd get from a nuclear deflection attempt in space. It's disperses very quickly through a huge volume of space, and it would never be undertaken in close proximity to the Earth.
And it looks like, unless there are any more questions, so please go ahead and send them to us via chat if there are. But we have one last question that kind of is a great summary. You know, not very many people have the title that you do of a job of a planetary defense physicist. So tell us what kinds of things you do today, day to day. What does your typical day at the lab look like?
Well, now, like a lot of us, since March 16th or so, I've been sheltering in place at home. So I've been finding ways to be more productive from home, and that includes running simulations on my computer. So I connect with my local laptop to a supercomputer that's on site at Lawrence Livermore and run simulations there. I connect with colleagues and help write documents to describe the work that we've done, either peer-reviewed papers or reports that go out to some of our stakeholders across the US government. We work very closely with different NASA centers, at NSA headquarters, which is our sponsor at the lab for a lot of the work that we do. The Department of Homeland Security also is interested in a lot of the work going on in planetary defense. So there's a lot of work coordinating between different areas that are working together on planetary defense. Making PowerPoint presentations to help visualize the simulations that we do is a really important part of the work. And starting a couple weeks ago, I've started going back into the office a little bit, but it's very like half days, a few days a week, just so I can get a little access different computers there for some of my work. But in general, if I was normally, in normal conditions, I would be doing a little bit more traveling. So there's a good amount of traveling. It's not always essential, but it's often, as we're finding now, especially face-to-face interactions are really important for connecting with colleagues. And I think a lot of us are missing that these days. So when we can, we try to meet face-to-face with our collaborators at conferences or meetings or technical interchange meetings. And a lot of it is planning for the future. So right now we're getting ready for the Planetary Defense Conference in 2021, which will be in Vienna, Austria. And we're hoping it'll be an in-person conference. But there's, a backup plan, as there is for everything right now, that it would be a virtual conference like the one that we're having this week for the DART mission. And there's a lot of folks that work really hard to pull off conferences like that. For the Planetary Defense Conference, we always have an exercise scenario. So Paul Chodas from NASA's Jet Propulsion Laboratory always comes up with the fake scenario of an asteroid that's going to impact the Earth. But it's based on realistic orbital calculations of a real asteroid type orbit that could impact the Earth if it were perturbed slightly. And it's always really interesting because they try to simulate not just how the scientists would respond to something that was a threat like that, but how the public would respond, how policymakers who lack, some of the science background would respond. And it definitely calls attention to the need for public outreach and engagement so that people aren't fearful unnecessarily, but have a grounded awareness of what the threat is really like and what ways we can be prepared to respond.
We have one final question. I think this must be from a student who heard you talking about Vienna and says, okay, I'd like to go, because this student is wondering if we offer, or if you offer, Megan, any high school interns or college interns that can work with you. How do they get engaged with you now on this subject?
We don't have high school interns, but we definitely have college interns, college and grad school. And we're even now with shelter in place, we had 2 people identified that we were going to work, actually, yeah, 2 people, both undergrad students. And we were able to keep their internships going, and that we'll do them, they'll start whenever they're a little after their virtual classes end. So I'll start in June, probably, both of those interns. And so we'll have a remote internship, and we'll be helping them the same way as we help our colleagues right now on WebEx or Zoom or the phone or email, Jabber, Microsoft Teams, all of our connectivity tools that we're using right now. And so we definitely encourage interested college students to apply to our summer program. The lab has a really great summer program, not just in planetary defense, but I think Planetary Defense hosts 2 students every year on average, and there's something like 1,000 every summer. And so there's all sorts of opportunities if you want to work on lasers or writing new computer codes or experiments. There's just a whole lot of things. So the area that I work in is called High Energy Density Physics, or HEDP. And if you Google HEDP summer program at Livermore, you'll probably find that posting, and you could plan to apply next year. They open it pretty early in the fall, I think, because they realize that a lot of the best and most interesting students often have lots of offers, and so it's good to be on top of it and look for it early on in the semester, I think.
Great. Well, thank you so much to everybody for submitting your questions, and especially to you, Megan, for sharing your time today. We just had a couple of quick points to make in closing before people log off and go about their day. We wanted to make sure you knew Megan is actually on Twitter. You can follow her. She's at Megan Impact, which I think is a really cool Twitter handle. So you can follow her activities both at the lab and in this industry if you're interested. I think we have a photo. Oh no, I thought we might show a photo of Jenny, her dog, but we can get to that. Maybe Susan, go back to the Lab Foundation. Just in closing, again, on behalf of the Livermore Lab Foundation, we were really pleased to be able to be part of this collaboration with the school district and with the lab. And for those of you who may not know the Livermore Lab Foundation, we've only been around about 4 years, but we were created specifically to try to inspire the next generation of scientists and engineers, and hopefully bring more students like a lot of you to the national labs. As you can see, Megan's just one example of thousands of scientists that are right here in our backyard doing amazing work. And there are often many opportunities for students to get involved. One of the programs the foundation supports is a high school internship program that unfortunately this summer has been disrupted, but please stay in touch with the foundation too, because we hope to be a real bridge to the school community. And we have a website. It's livermorelabfoundation.org. And we have a newsletter, so you can follow our progress and our activities and sign up for future events. As we mentioned at the beginning of this presentation, we'll have 3 more of these Ask a Scientist presentations. The next one's coming up this Thursday at 1 o'clock Pacific time. It's with Leland Ellison on Fun with Physics. And then we'll have 2 more next week on Tuesday and Thursday at 1 o'clock. So we hope everybody will have an opportunity to join us again for those. And I guess with that, we are finished. As I mentioned, we will be sending you a recording of today's event. So thank you so much to everyone for your time today, and be well. Thank you.